So okay, yeah. So we are all familiar with basic matrix notations, but just for sake of completeness, I'm going to denote with capital A the matrix and capital Aij being the ijth element of the M cross N matrix, right? So and now matrix product is defined as like we have A1, A1. This is our matrix Mn cross V. This is M cross N matrix, so we can define an conformability means like which where we can define the product. Like here we are defining like M cross N into N cross some P matrix, and in that case we can only define the matrix multiplication. So this is what I am calling as conformability of matrices. That is where products are defined, and of course sums. Like in case of sums, the order should be same. Like M cross N matrix is only addable to M cross N matrix. So in that respect, though there is another kind of product, namely the chronicle product, you might look at it where there is no such issue in like the order of the matrix. It doesn't matter, like you can multiply any matrix with another. Can I like allow all people to enter? Is there a setting in Google Meet like that?
Just check. I think in the host controls, like there was an option. Not sure if this will let everyone in, but like
Okay, let's see if
this.
anyone does enters, get notified now. But let's focus on the simple matrix product for now, and leave the chronicle product. So this is B. So M actually dot. So basically we just this matrix multiplication, we just like consider this as a vector and this as a vector, and we just take their dot product. So and this is the our like, so this is our first entry. So A11 B11 plus A12 A, A A1 to B21. So this is our first row element, that is so this can be written as like A1I BI1. So I equal to 1 to n summation. A bit clear. So this is our first 1 cross 1 comma 1 element on the matrix A cross A into B matrix. So now for any I comma j element in our product matrix, that is AB matrix, likewise we have AI n B n j summation over n. So if you just see, it's only basically the dot product uh, of that ith row in the first matrix in the A matrix and the jth column in the second, that is the B matrix here in this example. So 1 2. Okay, so here I have use of notation set. Okay,
Hey man, just a small thing. It might be nitpicky, but could you like make it K or something instead of N?
exactly. So this is basic matrix multiplication. Now now we will try to implement this on and the computationally, if you think that the matrix multiplication directly for an n cross n matrix, that is for the square matrix of order n, the complexity if you have is on3, big on3 to multiply algorithmically, and there is a better approach to it's probably o n power 2.3 or something like that, 2.3. So this is the matrix multiplication of simply just multiplying two square matrices. Multiplying two square matrices are by default conformable. So, but why are we so much interested in the finding the multiplying matrices? Like it occurs, it comes naturally in many fields, like uh, from the very simple system of linear equation, solving the system of linear equation, from to solving some ordinary some linear differential equations that we shall see in some subsequent slides. And it has also and similarly and in quantum mechanics too, like the equation, the Schrodinger's equation is like but in certain cases reduces to first order ODE. So and those operators comes naturally in there. But let's now try for example, just let's consider our Fibonacci sequence, like which all of us would have seen. F minus 1 plus n minus 2, f0 equal to f1 equal to 1. Now there are some people might now how to find the general term of this, like how what is the explicit representation of fn. One might suggest that finding the generating function and then solving the Fibonacci generating function. But this is a matrix lecture, and I shall give an example of using matrices to find the nth term of the Fibonacci sequence explicitly, and we'll see how the golden ratio comes naturally. So, well, we can write this linear recurrence, that is 1 comma 1, that is if you see fn the first term 1 and the 1 is being multiplied as fn minus 2, and so this 1 comma 1, like, so consider this matrix 1 1 0 1, fn minus 1, fn. Wait, did it did something wrong? Okay, no. So if you see like 1 fn, so this is the matrix we are getting again the recurrence for n greater than equal to 1. This is a matrix equation, the recurrence relation is getting reduced, right? Everyone got it?
Yeah, that makes sense. Yeah.
So let me write the last thing. F of n minus 1. So if you, we can recurse this, and like it should then reduce to fn plus 1 fn equal to like 1 1 1 0 something 1 1, that is for n equal to 0 and n equal to 2, that is Will it be n or n minus 1?
It should be n only because, like, if you look at the base case, right? If
Yeah,
it's
exactly.
f1 and f0,
Yes.
yeah.
So it should be n. So now it's coming naturally. We want to find the power of this matrix. So now one can see exponentially this is actually good approach even algorithmically when we if we suppose that we want to find the Fibonacci directly from on algorithmically we usually compute. Let me show you two approaches. Like one is the general approach, that is one is the generic approach, the simple approach, that is writing a function and then calling it like defining just like implementing this only fn minus 1 plus fn minus 2 and defining the best case f0 equal to f1 equal to 1. So and then directly as per for specifically in Haskell this type of recursive definition often occurs, and so uh, one should be very familiar with it. One knows it. So, anyways, the time complexity is here 2 power n. If you see, like for fn, we are computing fn minus 1, then fn minus 2, then adding them. For fn minus 2, we are again fn minus 2, fn minus 2, fn minus 3, fn minus 2. So now and then again adding. So in this way, the is getting and binary as a tree like formation is occurring. Now one can improve it like so-called the dynamic programming. One can we can store this fn since we are using fn minus 2 twice here, so we can actually store this in an array and in a stack, and then uh, we don't compute fn minus fn f n minus 2 twice. uh, so from starting from here and there, we just keep store f1 to compute fn. We just create a stack that stores all the f1 f2 f3 dot, 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 up till fn, and then we just use it. That is the concept of dynamic programming. This really like so. So then we would have to just yes, so here we just store this fn minus 2, and similarly for fn uh, I hope that's clear. Like even there the complexity gets reduced, and well, one might say, what's the complexity there? What's the complexity? uh, is the dynamical programming approach clear here, like in this case?
Yes.
Okay. Okay then, and okay then, like I don't know what does anyone came up with what would be the complexity there?
Space complexity should be higher, but time complexity should be lower.
Yeah, of course, the time complexity, but you might think that.
Actually,
Yes,
it would be linear. Well, linear in time and in space, it depends. You can implement it. Actually, we talked about this sometime back, even on the Discord server. You can implement it with constant space also. But in this case that you're talking about storing it in an array, it would be linear in space.
yes,
So,
it would be linear. Okay, so now we shall see, like in the matrix based approach, we would see that it's actually being logarithmic in n, and being logarithmic and actually kind of polynomial. Okay, wait a second. Would it be okay? Let's see. So so basically we have to just compute this, and now one one might now computing nth power of the matrix, one might suggest that suppose a is a matrix, and then the simple binary exponentiation technique, that is m is even then m by 2 into m am this one, and otherwise if m is odd, then minus 1 by 2 into minus 2 into a. So like, so one can see here that for multiplying two matrices of order say n, for order say n, one takes for multiplying this, for this multiplication one takes n cube, taking n cube, and then since there is like tn equal to tn by 2 plus o1, like for this, and similarly like recursing, we get that on is basically log 2 into like this time complexity of matrix multiplication, so that's actually log 2 into n cubed. So where n is the order of the matrix, I log 2, not log 2.
You mean log base 2 of m, right?
Yes, of n. Exactly. Log base 2 of n. So it's again even a better approximation, even a faster algorithm than the dynamic programming one. So now we would even like to like now this is what some computer can do, but at hand, as mathematician one might suggest that how to do this in hand, and so this is this is how the concept of diagonalization actually comes in mathematics. This is one of the path. I don't know historically how did it actually evolved, but this is an interesting path though, like coming to diagonalization from here. So if we basically somehow write this matrix, say any a whose power we want, and if we write this as q inverse a cubes for some matrix, and we are supposed to find this q matrix, and then if some d matrix, so this is a diagonal matrix. It is a diagonal matrix that is all whose element except the diagonal elements are 0, all non-diagonal elements are 0. So if this a can be written as this one, then a power n a power m can easily be computed as d power n or q. Now everyone is clear about this. So this now writing a in terms of this diagonal matrix, and actually if now I must introduce a definition here. Similar matrices, like a and b are similar matrices if and only if there exists q such that a equal to q inverse b q. One can easily see that order of a and b are always same, and this q should be like somewhat that the product is always defined. Like for that, yeah, I think it should also be of order n by n, right? If a is n by n, b should be n by n, and then q is also n by n, right?
Yeah. Are there any other conditions in Q than just being n by n? Like about of course it has to be invertible, so its determinant's non-zero. But apart from that, are there any other conditions?
Now, this is only a definition of similar matrices. If there exists such Q, then A and B are similar matrices. When will such a Q exist for every matrix A? That's the question of diagonalizability.
No,
And
that's not what I'm asking. I'm asking there exists a Q such that fine A, but what kind of Q does it have to be? Is it like we know that fine for the inverse to exist, it has to be an n by n matrix with determinant non-zero. But apart from that, are there conditions that Q needs to satisfy for this whatever definition? Like,
I don't think so. Like I think like isn't it like as doesn't it form make sense? Like there exists a Q such that if there is a such q which is like any matrix whatsoever, of course it should be invertible for its inverse to exist, and q is invertible. Let me write that, invertible. I hope that's enough condition. Like I don't think there's much to it. A and b are similar if and only if there is this q invertible such that a equal to q inverse bq.
Got it. Got it. Okay.
So
No other conditions. Okay. Got it. Thanks.
so if this if for q now if a is similar to some, actually one can actually see like actually the matrices actually comes from formal way to introduce matrices are one can see that enclosing matrices actually form uh, the vector space, like it's isomorphic to Rn squared, Rn cross Rn squared. So one can see that. So it's actually isomorphic to Rn squared actual, and uh, if one like now consider we have vector spaces V to V, which is like m dimensional to n dimensional. This is a vector space, m dimensional vector space, and another V which is like okay, call it abuse of notation again. Call it W, and dimension W is small w, dimension V is small v. Okay, so now consider a linear transformation from V to W. Now actually there exists an isomorphism between this set of all linear transformations to the set of all matrices m cross n or w cross v or v cross w. Wait a second. Well, it should act on the matrix should act on the space V, so like it should be so it
It'll
should
be an
be
n cross m only. Yeah.
yes W cross V, right? V cross W, right?
Oh yeah. Yeah. So, yeah. Exactly. V cross w. Sorry.
So
Yeah.
it's actually isomorphic. These are isomorphic, and which is in turn isomorphic to V cross W space. So these are again isomorphic. So why did I introduce? Yeah, so actually I introduced it because like one can see like the similar matrices actually if A and B are similar, like we are actually changing the basis here. We, one like the isomorphism is actually uh, like V has say basis ek and W vk cap. Okay, these are one basis of V. Now there exist multiple bases actually. Now similarly for W I define wk as the basis. Okay, wk basis, and so when the isomorphism comes naturally, that is uh, for L something in V. Okay, now it's really getting obvious. Okay, yes, x belongs to V. X is vector. X can be written as summation, say, ak vk cap. Similarly, y belongs to W. Y can again be written as summation bk wk cap. So this is how actually the so for due to linearity we have ak lvk, right? So this ak is actually forming like the yes. So this ak is actually forming the kth like what to say, the row vector, the kth row vector of the matrix. This is the usual isomorphism, that is this is the kth row, and when it is composing over this set, A1 dot dot dot. This is the matrix. This is the kth row. Okay, so kth row. This is our representation of a vector in the AV in the with respect to this basis set vk cap. K is less than equal to v less than equal to 1 dimension of v vector space, and so this yields some value in vector in W actually. Now I've chosen this WK actually is pretty specific, that is LVK cap equal to WK cap. So this is a pretty specific I've chosen. So this is V cross yes multiplying actually wait a second. So this is a special case actually. I am here both the dimensionality of the vector spaces are same, so like both are basically there exists an isomorphism, even there exists some isomorphism between them, but sometimes the matrix all the row vectors aren't zero. If some of the row vectors, like let's say k is less than, like v is less than w, in that case v is less than w, in that case for when k exceeds v, actually we can't define like this. We will have to introduce 0 0 0. All the k through beyond this k actually is 0. So does that make sense? So like in that respect it is okay. Does that make sense? Okay.
Yeah, like
So so okay, basically this is, and so let me try to be a bit precise here. Okay. So V is a vector space with Vk the basis Vk a less than equal to 1 less than equal to V W vector space k less than equal to W less than equal to 1. Assume V is less than W for now. The other cases would follow similarly. Now, so the linear transformation V to W sends Vk equal to Wk, k less than W. Okay, so basically one can easily see that the uh, image of L has a dimension, again V, and kernel by rank nullity theorem, nullity, that is the dimension of kernel. By rank nullity theorem it would be W minus V for. So when we are considering this is the equation, and when we are basically considering the matrix representation of L, the usual isomorphism between L and the matrices which call M, the matrix representation actually A11, A1N. Wait a second. this would be yield a vector in W, right? And since this representation is basically with respect to the vector V, that is the coefficients of V when we write the elements of the vector space V, and this representation in W is the representation in forget this actually, like this is probably wrong. This is, we won't need this. This is enough. So basically this if this is m m11 m1v dot mw1 dot mw, so and this suppose be 1 dot pw. Now this matrix product is correct, and so I was just trying actually to point out the isomorphism between the vector space of trying to represent the explicit isomorphism between the vector space between dimension m to n here in case v to w vector spaces, that is v to w vector space whose dimension are small v and small w respectively. There exists an isomorphism that was clear from this only, that they both are like isomorphic to this R V cross W set. So there will exist an isomorphism. Now I was just trying to actually explicitly mentioning this isomorphism and how does it actually comes naturally in the study of vector spaces. And actually this is the formal matrix representation of a linear transformation, and somewhat deviated far away from the Fibonacci series. So if you see, this is actually a change of basis. We are actually writing one. Okay, now I'm just this one can verify as an exercise. A, B are similar if and only if A, B represents same linear transformation. So this is basically like one can say the significance of linear transformation, similar linear transformation, and but in this case we are somewhat into the applied aspect of this theory, and so the computational aspect. So and okay, so now let's try and find the this matrix Fibonacci matrix and Fibonacci sequence I just discussed, that was 110 matrix for if n minus 1 equal to if n minus 1 minus 2. So this is the basic writing down the linear recurrence of the Fibonacci. Now algorithmic Fibonacci has just I described the simple method, the dynamic programming method, and the matrix method, which we saw O log n into k cube multiplicity, where n is the nth Fibonacci number and k is basically the order of the matrix. So for Fibonacci it's like 8, so 2 cube 8, so like it reduces to 8 log n matrix multiplicity, I mean complexity, time complexity. So that's pretty better like than a dynamic programming and simple method. So the matrix exponentiation, as I discussed, that which is like the binary exponentiation applied to the matrix exponentiation, that is dividing the cases into odd and even, and if it's even, like as I mentioned in here.
But like there is still a trade-off here, because to do this properly you also need log space, right? Log time and log space. But in with the dynamic programming and without using the array but just using two variables for fn and fn minus 1, right, you can do it in constant time. But over here you have to, you will definitely have log time to store all and space to store all the matrices. So there is that still that trade-off that's happening over here. It's not unilaterally better.
I hope still the time complexity is better, like implementing this on the just computer and then like finding like the 1,000 Fibonacci number or like the 10,000 Fibonacci number. It relatively gives a quick answer than dynamic programming. At least the one I described here, storing using that array or stack list. So, I hope.
No, of course. I mean, like obviously, like on a modern computer, you would choose that log one because memory is not as much of a problem anymore. But
Yes, yes, of course. The time complexity is lesser here, not the memory. Memory is might be the space complexity is a bit large here.
no, what I wanted to point out is that this trade-off happens, and it's quite fascinating, right? Why it happens? Like it raises deeper questions about algorithms in general. So, yeah. Sorry, if that was.
Actually, this it would be better if you all actually interact. So that's cool. Yeah. So this one, the matrix initiation part. Yes, this one is the matrices formation part. Okay, so now eigenvalues and eigenvectors. Now, so basically, if we have a matrix, suppose like uh, matrix which can equivalent be called linear transformation, then if we have this for suppose this is an m cross n matrix, so basically it's to wn, like this is a vector space of dimension m and this is a vector space of dimension n. So if this is the case, actually the both will actually it would it has to be a square matrix for this to happen. So like this is also lambda x, so basically I have to write here n plus n, actually n plus n, so t plots v to v. If in that case, if somehow the matrix preserves the direction of the vector it has acted, then the vector is called the eigenvector, and this the scalar multiple is called the eigenvalue. So basically, so now here's an elementary observation, that is t power n x equal to lambda power n x. So this is easy to see. Now, so matrix
It isn't necessary that every linear transformation uh, has to give eigenvectors and eigenvalues, right? For example, rotation matrices don't give eigenvectors.
rotation.
In case of except like 180-degree and 360-degree rotations, you can't get any vector where t of x is equal to lambda x.
Well, actually, you can get if you not restrict the scalar field to real. In fact, you can get probably there will exist for the scalar when the scalar field is complex field. Just
I think even that would only be true if you are considering just simple real numbers and multiples of I. Even that would only work when in R2. Otherwise, it won't work.
I didn't get it exactly.
Like you said that if we use complex numbers, then we should get eigenvectors and eigenvalues every time, right? I think that might not be true if we use like any vector space with more than 2 dimensions. Like in 3D, you might be able to make a like change in orientation from where you cannot get using simple real numbers and complex numbers.
Here is the this eigenvector is the existence, like there should exist a vector that's get preserved, like and you were saying that there won't exist such a vector. Is that your
There
question?
might not exist such a
Okay,
vector.
there. Okay, we'll have to see that then. We'll
No,
talk.
like, doesn't it depend on whether you can diagonalize a matrix for the existence of an eigenvalue? Sorry, for the existence
Actually,
of
it kind
an
of,
eigenvector.
if the eigenvalues are distinct, it's trivial to see that what the for distinct eigenvalues, this is our next theorem, that the for distinct eigenvalues, the distinct eigenvectors would be actually linearly independent. The set of eigenvectors would be linearly independent, and if the eigenvalues are distinct, then it's easy to see that the diagonalization is also possible. And sometimes if the eigenvalues are not even distinct but have a algebraic multiplicity, so that the number of distinct eigenvalues plus adding all the like in we count all the eigenvalues with their multiplicity, and if that's equal to the dimension of the underlying of the domain vector space, then the matrix is diagonalizable actually. So that's more generic, and probably that's the most generic, I don't know. Yes, but that's true.
Right, but like take like the example Shubh just brought up, the rotation matrix, let's say even in 2 dimensions, right, for R2, if you're willing to entertain this, right?
Yes.
Like if you like sorry, what if you solve that, it'll be what cos what the determinant of that will be cos squared of x plus sine squared is equal to 1 or something like that, right? Like when you're solving for the
Like
eigenvalue.
just say that I just forgot the rotation matrices.
So the rotation matrix is cos. The first row of the rotation matrix is cos theta, and sine theta. It doesn't matter. Minus sine theta or sine theta doesn't matter. The next one is minus sine
Minus
theta,
sine theta, and
and then cos theta. Right. So when you're solving for the eigenvalues of this
determinant equal
matrix,
to 1. So actually,
no, yeah, the determinant, yeah, it'll definitely be equal to 1,
for
right?
so
So
this is non-singular, and so the
yeah, it's not singular, yeah.
eigenvalues are actually are distinct and belongs to complex. So there will be
Okay,
eigenvectors, and this is our theorem that we will come like.
I see.
Okay, like let's discuss this first then.
Yeah, this is a compare. Wait, so 1 second. To solve for the eigenvalues of this matrix,
Yes.
you have to basically take cos theta minus 1 and preserve like those two sine and minus theta, and the cos theta minus x.
Find the eigenvalues. We have a polynomial actually, the characteristic polynomial.
Right, the characteristic polynomial only for this one. 1 second. So now that he did bring up this issue,
Cos theta
it's
minus cos theta equal to sin theta sin theta. So and 2 cos theta lambda plus f. Is there anything there? Anything left? Plus lambda squared. So lambda equal to 2 cos theta 4 cos squared theta minus 1 is 4 by 2. So you can see that
yep.
actually it's complex, unless the theta
Yeah.
is where you said the irregularity is that 180
Mhm.
degrees or 90 degree or something like that.
Yeah, exactly. It'll only be one for that. So in this, not for 90 degrees, right? Only for 180 or
180 degrees
360,
exactly.
right? Yeah. So
I,
oh wait, okay, fine. You just multiplied those terms. Yeah, all right, and so you do in fact get eigenvalues, and you will be able to get eigenvectors.
yes.
But the entries of those eigenvectors are also complex numbers.
Yeah, so we are assuming the field where we are considering the matrices, that is the underlying field of the vector spaces, are itself the complex field. So we are allowed to get the uh, entries complex, right?
Okay.
Okay, so this is
So we
the theorem I just used, so I'm just stating it then.
So based on his question again about if you have an n by n matrix and if it'll always be like let's say if it'll always have what is that
If you said unitary matrix.
no, I'm not talking about unitary matrices.
Uh,
Yeah, this would be an example of unitary matrix, right? But like you would necessarily have eigenvectors if you only like if you consider the complex numbers, right, as your base field. Otherwise, you may not be guaranteed the existence of eigenvectors.
yes, it's here in this case only the eigenvectors will not appear actually if you consider the base field as real on.
Right, right. So in your previous example, right, like sorry, your previous slide, right, when you're defining this,
Yes,
right, as a map from V to V,
yes.
right, does the base field of V have to be the complex numbers or the matrices that you're mapping, like associating T with, right, are they over the complex numbers? Like the space of n by n complex matrices, or is it like vectors,
Okay,
like
okay, I
vector
see.
space
Yes,
over C?
actually, it would be C n
Yeah,
cross n, the space of n by n complex matrices.
I
Uh,
see. Okay. And
so
what about V? Can V also be defined over any field or
suppose V is since V is suppose V has underlying field real, then but we are composing it with some complex entry on the matrix, then again it's mapping into V, so we can see that V is not again, we can see such vectors where V is not necessarily again keeping it real, so it's also automatically complex, right?
right, right. So this only works actually over the complex numbers.
Yes, yes, of course, in any scalar field, but in any field actually, but it works in complex field. I don't know if something which is
Sorry.
if that is the best uh, field probably to work in. I hope that this is the best field. Like below complex field, we can't have this to be always true. That is for every eigenvalue there will be eigenvector for any linear transformation. That is.
And actually, sorry, one thing earlier, I think I only made this mistake about saying this, but the matrices can be R n cross n also. Like, the space of matrices doesn't necessarily have to be
No,
complex
no,
matrices.
just the for existence of eigenvectors and eigenvalues for any matrix, then it would. I mean, okay, let me state it this way that in the CN
No, the
cross.
matrices can be defined over any field,
Yes,
right? But
right.
the vectors need to have complex whatever. Like the
I
vectors need to be defined over C.
Is that necessarily like in this example? If we are restricting, if we are considering even the complex vector space, that is okay. In this example, actually, uh, so the matrices have to be the complex field. The underlying field of the matrices should be complex. Cn cross n. It not necessarily this should be a complex field or its underlying field need not be complex. For this example, this maps this M maps R2 to R2, right? Okay, no, even they have to be the complex. Yes, complex. Both have to be the complex actually. In this case, you said that the eigenvectors would come in the complex field, some complex vector space, and
Well, the matrices themselves, they can map C2 to C2, but you only have the existence of eigenvectors if you're considering C2 to C2, not just R2 to R2. Even the matrices themselves could have real entries, right? Like in this rotation matrix, it'll always have real entries,
yeah,
technically.
yep, yes,
But oh yeah, although to define the characteristic polynomial, you need to include Cn and cross n also. Okay, though this is a little subtle. Uh, I am so I think we're being a little pedantic, but I mean, I guess it's good to clarify this.
yes, definitely like
Um,
so. Okay, let me just state the theorem just for completeness sake, like, and the proof of that. So A is matrix, lambda is its okay, so A minus lambda I, consider the determinant, is equal to 0 if and only if lambda is taken. Now I'm just sketching the proof. That is a minus, so a f equal to lambda I, lambda v basically, the one way. Okay, so actually this is the other way, the way I wrote. So okay, so f equal to lambda v. So basically consider this as a matrix A minus lambda I into v equal to 0, right? These are equivalent, these two statements. So now there exists v. For we are assuming lambda is eigenvalue, so there exists v, namely the eigenvector. For this to happen, so basically this is again a matrix which is singular, which doesn't have any inverse. So basically the determinant of this matrix is lambda I is 0. So this is one way. And now suppose if and only if. So now suppose this happens. Now lambda is like there is a lambda, there exists lambda such that this happens. Then basically there will exist a v again, since this matrix is singular, since the determinant of if a determinant of a matrix is 0 if and only if the matrix is singular, that is non-invertible. So in that respect, will there exist a v which we will again call the eigenvector, and so again retrace the steps back here and we get here lambda is the eigenvalue with respect to the eigenvector v. So this is our theorem, and we already use this theorem here to find the eigenvalues of the rotation matrix. So lambda. Now as an exercise, one can try and find the eigenvectors too with respect to this. Consider one lambda, consider the plus one only. Okay, so actually let me just write it here. Right, so good to see the this complex. Actually now one can, this is might be a tangential, but one can see that magnitude of this eigenvalue is basically 1, right? This is the complex cube root of maybe for a rational theta it will be complex cube root of some unity, and so this is basically nothing but the eigenvalues actually lies on a circle actually. So for each theta, so actually in a family of this for every theta it defines a family of rotating matrices, right? So all of whose eigenvalues are magnitudinally lying on some circle. So actually this is something kind of related with what is known as the spectral radius, like where the eigenvalues of uh, the supremum of the norm of the eigenvalues of a matrix, of a given matrix, that is the spectral radius basically defined, and that it would exist. This is somewhat related to the Grishagoryn's disk theorem. That one I probably won't be able to point that in this lecture, but one might just Google that. It's interesting to see. Okay, so now just now next theorem is the next theorem. If lambda 1 dot lambda n are distinct eigenvalues of Enclosing matrix, then A is diagonalizable. So actually, that time I just pointed it out and somewhat tried to say the more general theorem, but here I'm restricting to the somewhat weaker one. So that is no, A is diagonalizable if now that is A is similar to D diagonal matrix. D is the diagonal matrix. Okay, so that is one knows that is there exists Q such that A equal to Q. That is there exists Q. It is such that A equal to Q inverse BQ. Okay, now this is a theorem. Like one will easily see this after an observation. That is, let me just write it out. Define Q. Now Vk here is the eigenvector with respect to eigenvalue lambda k. Okay. So basically this is the matrix, right? Like n cross n matrix actually. This is a column vector actually. So this has components say v1, 1, v1, first row, second column. So second row, first column. So dot dot dot. Nth row, first column. So in this respect, right? So this is actually a matrix. And we would actually why I'm writing this Q is because observe that if we define it like this and lambda k are again the eigenvalues of A, and since the eigenvalues are distinct, they has assumed, so the eigenvectors are linearly independent and by default it would be distinct. So, now actually that's a theorem that one that the eigenvalues are distinct, then the eigenvectors would be linearly independent. Can everyone see that? The eigenvectors will be linearly independent.
Yeah.
Yep.
Okay, so linearly independent. So basically, AQ equal to QD. This is our claim. Because so this is our matrix and this is our Q. So if one considers this row with this column, that is, this is a V1, right? This first column is V1 and this row. So basically one gets again some lambda times V1. So that's basically again actually lambda 1 times V1. So which is basically V1 vector, V1 vector. Now one can see this, right? This clear, right? Like why that is happening? Hello, is that clear?
Wait, you mean the?
Yes, this AQ equal to QD. That's this one.
Oh yeah, yeah.
So this is clear. And then if Q is invertible, we have assumed that in the theorem. So oh sorry, we haven't. Basically, Q will be invertible since the eigenvectors are linearly independent. So basically, they are forming the matrix, and the matrix they are forming is non-singular. So the determinant will be non-zero, and thus, or in fact, they will be non-singular. So the inverse exists. That is, so Q will be invertible, and what was our AQ equal to Q? So basically, A equal to Q dq inverse. Since Q is invertible, it doesn't really matter. Like the matrix would be different, but that one can also write Q inverse dq with Q being replaced by Q inverse. So that's the thing, right? So this kind of proves this theorem, right? Like there will exist. Right. Okay. Yes. So we show that we just show that this D, the diagonal matrix, is nothing but dot lambda n, the eigenvalues, and that Q is nothing but let me just change here a bit. Okay, so in that case, Q would be like this vector, right? I mean, matrix. These are all vectors, column vectors specifically. So then, now we are ready to attack the Fibonacci problem. So once we know this, power of diagonalized matrix, that is relatively simple to calculate. Like if lambda 1 dot lambda k is the matrix, then power n is equal to all the other integers are 0. So basically lambda 1 power n dot lambda k power n, right? This is a simple observation. Fibonacci again. So okay, so our matrix was 1 1 1 0. You compute the eigenvalues, and this is how the golden ratio will appear. So 1 minus lambda 1 square into lambda square minus lambda minus 1 equal to 0, lambda equal to 1 plus minus root over 5 by 2. So this is called the golden ratio, right? 1 plus root 5 by 2 and 1 minus root 5 by 2.
Yes.
So basically, okay, so we got the diagonal matrix we wanted. So basically, the diagonal matrix would be, which is the matrix is similar to 1 1 0, similar to 1 plus root 5 by 2, 1 minus root 5 by 2, 0 0. We got this, and now we want to find the Q. Basically, we want to find the eigenvectors. Now the eigenvectors are easy to calculate, right?
Yeah, you just solve like two.
Solve the n
Most,
linear equations,
yeah,
and
yeah.
so may I leave it like here in this case?
Like if you have x, let's suppose your vectors x and y, right? Like matrix
I'm
one
just
one one
writing the
zero.
system of equation and then leaving the calculation. Okay.
Yeah, yeah, yeah. I mean, of course.
Yeah. So like,
You don't have to. Yeah, of course, you don't have to calculate it.
so basically, we just want to basically, okay. So 1 1 equal to x y equal to lambda x y.
So if we can write it in the computer, then this will be constant time.
Uh, uh, well, this diagonalization process and this basically finding what's the time for calculating the polynomials of a equation, polynomial equation?
What do you mean powers of?
Yes, nth polynomial, nth degree polynomial.
You can do it in log n time. Wait, like if you want to calculate any constant to the power of n, you can do it log n time, right?
Yes.
So this would also be logarithmic, except the factor would not be 8, it would be smaller, like it would be 1. So it's faster than actually multiplying the matrices.
By binary
You know,
exponentiation.
yeah, you can do it in binary exponentiation, but that 8 factor will not come. So this is a lot. This is significantly
Yes,
faster.
so a lot of studies haven't been done like just like that on diagonalization, right? So anyways, okay. So this simply reduces to solving this, and in fact, this is one can see like a similar to an apart triangle, not similar, not technically similar, like literally similar to an apart triangle matrix. So basically, x plus y equal to lambda x. So, so we have to find the non-trivials basically. So, yes, so basically one can find the non-trivial zeros of this equation from here, right? So one thing I forgot to mention that in the eigenvalues and eigenvector case that eigenvalues we don't accept 0 as eigenvalue and 0 as eigenvector. Also, you probably wrote that in the definition, the notes I sent on Discord. So anyways.
Oh, you sent the notes.
Yes,
Where?
yes. Okay, I will reshare that. Anyways. So basically this is it. And yes, it's of course faster than directly computing the values.
I think where this would make a massive, like really massive difference is that if you had something more complicated in the Fibonacci sequence, let's say n terms depending on n other
Okay,
terms.
the general linear recurrence, right?
Yeah. Okay. So okay, you're getting to
Okay, now
that.
so in that case, an is written as some suppose. Okay, let me write c1 a n minus 1 plus c2 a n minus 2 plus dot 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 ck a n minus k, right? These are the coefficients, and given a0 a1 dot 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 ak minus 1, this k elements are given. So basically the Fibonacci sequence is just c for k equal to 2 and c1 equal to c1, right? c1 equal to c2 equal to 1. So this is our Fibonacci. So this is the general recurrence relation, linear recurrence. One can even like solve this with even with simple generating functions too, but again this is a matrix talk. So
And what would be good about this, right, is that it would, like, yeah, exactly, it would be k cubed log n, right, if you just used it like that. But if you pre-computed, let's say the eigenvectors, sorry, yeah, exactly, if you pre-computed the eigenvector, right, then that would just be, doing that n cubed once. It would be n cubed plus log n rather than log n times, sorry, k cubed plus log n rather than k cubed log n.
this is right.
Yeah, exactly. Rather than k cube times log n. So
Yes. So we'll have to see. Yes, of course. This is better than just like brute forcing and computing the exponentiating the matrix. So, now we are interested to find the matrix here. What would the matrix appear in this case? Can anyone can guess? The second, third rows would be 0, 0, 1, dot, dot, 0, 0, dot, 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 okay, 0, right? And this is what? Okay, so CT k minus k, k minus k2, k minus 1. Now this first row we are is the trick, right? This is a k cross k matrix. So one can easily see that it would be C1, C2, C3, dot, 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 Ck, right? So this is easy to see, right?
Yeah.
Okay, thanks. Just tried to switch the windows, but it didn't happen. So anyways, so again, the process would be similar. In that case, we would just uh, actually, can you mathematically think of any easier? Do you really think that this would be easier to compute the characteristic polynomial for this? To compute would be easier for this kind of matrix whose like diagonal entries are 0. Actually, it won't be 0, or will it be? Well, it won't be 0. Yes, it will be 0. The diagonal entries will be 0. The diagonal elements are 0, but still we have a 1 in here. Someone.
Wait, that one isn't on the diagonal though, right?
No.
Like
Yes.
it's just the C1 and all those zeros, so it'll just be minus C1 to the power.
It's one below the diagonal.
Yes, it's 1 below the diagonal. Oh, yes. So how to compute the determinant? It would be like C1 minus lambda dot 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 minus lambda, and so the determinant.
The right column is all zero except the ck, right? So it'll only like you only need to check the ck and the smaller part of the matrix to check the determinant.
Yes, the right column. Yes, the right column is 0 without the determinant. Yes. This one. Okay, so you are talking about this matrix.
It's just the k minus 1 order identity matrix. So that term would just evaluate to ck or minus 1 to the power of k times ck.
Yeah.
So and it's actually
Well, minus
like
1
an,
k minus 1.
what I'm trying to say is the polynomial won't be that not nice. So like it would be a nice polynomial. So I think it's easier to calculate actually. Like so it was not planned, but just thought that okay. So okay. So this is okay so far. Like now I would just present some applications on differential equation, and like yeah, I know it's way past the deadline. It's like 20. I'm like 20 minutes late of that. So may I continue or?
Yeah, continue.
You can continue.
Okay,
Yeah.
thanks. So okay, now interesting application is the solving the system of differential equation. Like we have all solved simple differential equation like what is y equal to some y prime equal to y. So this is all what we all have studied, right? It would be some exponential, like it's simple. Okay, I'm just leaving it. Yeah. So right now, what about this system of differential equation? Uh, x1 prime equal to something, say x1 plus x2 plus x3, x2 prime equal to say x2 plus x3, x3 prime say x3. Okay, now how do you solve this? Like this is only trivial because this is okay. Let me add some another extra x1. Okay. So x1 plus x3. Now how to solve this? this is the problem. We shall see. This is extremely simple once we have got those techniques at hand.
I mean, do you assume that each x is some kind of linear combination of exponentials, and then
No, I
you
don't
know?
assume. I won't assume here. I would just write it in matrix form. And okay, so I'm just introducing notation x1, x2, x3. Okay, this is a matrix x, say x vector column matrix. Okay, I'm just writing x. Okay, like you will have to assume this is a vector. Okay, so and x prime is basically nothing but x1 prime, x2 prime, x3 prime, with respect to parameter setting. Okay, so our matrix reduces to basically, what was our matrix then? Like
It was 111,
x1,
011, 101.
0, 1, 1, 0, 1. Okay, so this is it, right? Now we would, if we kind of diagonalizes this matrix, say this is an A matrix, and suppose we find some Q inverse A Q x equal to x prime, then we like take this x in here, and this reduces to somewhat Q x prime Q. But are we allowed to do that? Yes. No. Qx equal to AQ. So right, it's fine. So okay, then if this is once we if this is a diagonal matrix, Q inverse AQ x. So this is diagonal. This is the diagonal matrix. So this basically reduces to dx. And now if we define qx equal to y, acha, q is constant coefficient, right? Like okay, these are only valid for the system of differential equation where we have the system of differential equation linear and constant coefficient. So this is, the validity is quite restrictive. So in that respect, so if we have a constant coefficient matrix, then we get qx prime. This is one thing I would like you all to check, and this is really simple. So if we are cool with it, then we somewhat the equation reduces to x prime dy, and the
Wait, could you just go back to that slide 1 second? Like, uh, cool.
so in here y equal to dy, y prime equal to dy. So basically this is a diagonal entry, say lambda 1 to lambda n, using a lambda for we just saw that they will actually be eigenvalues when the eigenvalues are distinct, and so and y prime dot 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 y1 prime dot 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 yn prime. So this reduces to the simple differential equation we all know to solve, lambda prime equal to lambda y1, y2 prime equal to lambda y2 dot 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 lambda y3 prime equal to lambda y3 dot dot dot, so and so forth, right?
yep, works. And okay,
Once
so
once we know the y, then we can just find this since q is invertible, so we can find s from y, right? So yes, so it would eventually be a linear combination of where e power x, where x might not be always real, and that's why we sometimes actually it's actually like sometimes okay, this solves the question of why in a simple harmonic oscillator we all saw in class 10 plus 2 that in a simple harmonic oscillator the equation comes as we usually take the one term as that is solving this equation.
You take it as e to the I omega t.
So right, yes. So actually this can easily be converted to this type of system, right? The y prime equal to minus kx and then y equal to y prime. So this is linear. This is this kind of ODE.
No, any linear differential equation with just one like dependent variable, right? Like in terms of y, let's say, because of the fundamental theorem of algebra, if you assume that y is equal to e to the power, let's say, lambda x, right? What happens is that you just get powers of lambda, right? Which are the coefficients, right? Times e to the, you can factor out that e to the lambda x and just ditch it, right? And then because of the fundamental theorem of algebra, it'll have solutions. So you can, it's legal to assume that,
Yes.
right? So okay, nice. This is pretty cool though, like, you know, e, e to the
I
lambda
was
one.
just pointing
Yeah.
out that E might be complex. That is how the trigonometric solution appears in this equation, in this linear harmonic oscillator equation. Since E is complex, so the cos theta terms or the sin theta terms, is writing that from the De Moivre's theorem. Yes, De Moivre's. Or like from the e power I pi or e power I theta equal to cis theta. From that, it follows actually. So anyway, so like let's solve this for a bit for a moment. So basically, I shouldn't have taken this random cubic polynomial, which I probably won't be able to solve in here.
Hey man, don't worry about solving the
Okay,
equation
okay. So
for us.
you all got the algorithm right, like how to
Yeah,
solve
yeah,
it.
yeah. Yeah, yeah, yeah. You don't have to crunch it out.
Okay, cool. Now this slide I somewhat prepared in the like I was like learning a bit of quantum mechanics, and the first thing that came was the notations. Like they use the linear vector spaces, but don't tell later. Yes, of course they do. Like, but in different notation. Like I don't know how much I will be able to tell about it. Like in quantum mechanics.
Hey, listen, man, I'm sorry. I just have something to clarify about the previous topic
Yes,
only.
yes, yes.
Like, because each of the y, like, you know, let's say y vectors, right? Y can be represented as a linear combination of e to the lambda, you know, I, right? Like
Y
all of
vectors, right?
those.
You are considering the this one, right? Like or this one. I made a distinction that is x is after some transformation y.
Okay, sorry. Let's. I mean the x's,
Okay, okay.
right? The x's, like all of the x vectors, can be represented as a linear combination of e to the lambda some substrings, lambda ix. Or okay, let's not confuse I, because I over here could be complex. Lambda jx, right? Like
Yes, yes.
where lambda j are the eigenvalues of the, you know, which
Okay,
matrix A.
okay. Why is this? How can we assume that
No,
directly?
no. The reason, no. The reason I'm asking this is
Okay.
like, you know how each of the y, right, can basically be the solution of each of the y's is e to the lambda, like yj is equal to e to the lambda j t, right? If t is your independent variable, like
Yes.
when you solve it,
Yes.
right? So, and of course you can, like, the x vector comes from doing applying a matrix to the y vector, right?
Yes.
So the x vector is the matrix A times e to the lambda 1x all the way till e to the lambda
Okay. Let me write
nx
it. Well,
and
give me one second.
t, sorry.
Okay.
You can basically write x, right,
X.
equals a times the column vector consisting of huh no,
B.
not x prime. Just draw the column vector, like the column vector in the first entry is e to the lambda 1t
Okay.
until yeah, e to the lambda nt.
Okay. So
So you can sort of think about X as being an element of a vector space with that e to the lambda 1 t till, with that being a basis, right? E to the lambda 1
yes,
t 0 0 0
yes,
0 e to
actually,
the lambda 2 t 0 0.
yes, because they actually they all are functional spaces which are functionally linearly independent. With that, the function spaces, if you say, right? Okay, okay. So continue.
So, okay, yeah, exactly. That's what I wanted to know. Is each of the X entries, right? Like, could you write down, let's say, X1, for instance,
Okay,
right? Is
some
basically
linear
just
combination of this.
right. It's just
See,
all the row A, entire A1 row. No, it's just the A11 till A1n row dotted with, yeah, yeah, exactly. It's that, right? So, are the X, all of the X things, if you consider it as an element of a vector space with that those exponentials as the basis,
yes,
will the X's be linearly, you know,
independent.
they should be, right? Like, I just wanted to confirm that they should be linearly independent, right?
Well, if if A is non-singular, it probably will be.
Okay, fine. Yeah. Okay. Sorry. This was a trivial question. I shouldn't have bothered you with it. My bad. Yeah. It will be linearly independent. Okay, maybe that's another way to interpret this entire problem, right? If you say that this differential equation can only be solved if the xi form a linearly independent set
Yes,
over
can.
the.
Yes, actually, the general solution will, if you consider the dimension of the general solution would change when the A is not singular. If A is singular, then the dimension of the linear, the general solution, the space of the general solution would be n-dimensional with respect to this functionally independent bases. Okay, right, basis.
Right. Yeah.
And if that is non-singular, then the some nullity will come in, and the image of this A, since the image of this A will actually be the probably the dimension of the general solution,
Well, you
right?
mean the other way around, right? You mean if it's non-singular, they will all be functionally independent because.
Yes, it will be non-singular. Okay,
Yeah. Okay.
I just
You meant that. Okay.
I misquote, right? Maybe. Okay, sorry. Okay,
Okay, so this is crazy, man. Like you start with one vector space for, you know, there's so many different vector spaces over here. Like there's of course the formal vector space whose each, element consists of the function, right? Like let's say n vectors of functions. But you have an actual vector space whose basis is these functions, like e to the lambda t, right? So you have all these different things
actually,
built
you
together.
can like in this case, if you want to know the underlying vector space, it's nothing but the for probably the L1 space. L1 space, if I'm not wrong, the space of all the functions which has continuous first order derivative is nothing except that. And in somehow in that space, the e power lambda 1 t lambda n t they forms a basis. So that's
Wait, is it the space of all L1 functions? Is this enough to form the space of all L1 functions, or like does this span entire L1? I don't think so,
no,
right?
I don't think so. Like it won't span. Like L1 function is infinite dimension. It's the general solution only forms an n-dimensional vector space. Okay, vector space.
Oh shit, man! I just had an interesting thought. Like, what if we take like all these n by n matrices, right? Let's say, like they have their whatever all like diagonalizable matrices, right? They
Okay,
have an associated basis consisting of e lambda 1 till e lambda n, right? If you consider all these systems of differential equations, right? The
okay. So
intersection
yes,
or the union, sorry, disjoint
union
union.
of the general solution, right? You were talking about.
Yeah.
I don't know
Will
that
that
would
form
form
L1?
a L1 vector space. The whole that would span the L1 vector space or not. Maybe we can ask the tomorrow.
Yeah, that's what I want.
So
Yeah.
note it down. Probably I will after this. Okay.
Yeah, I'll also note it down. Yeah, we'll talk about it later.
So
So cool. This
so
is
this is okay, right? Like everyone is getting it right.
um.
Okay, so
Sorry about the interaction. I know you wanted to start some. Yeah, this one,
no,
but
actually, Konna just this is the open problem that I was supposed to. I will actually, and this is like just a I don't know. I don't know much about it in that sense. So, I just wanted to make a point in the application of linear algebra in quantum mechanics. Like the thing I actually that baffled me a lot is that's a notation that is this is the Kate notation. So this is the Kate notation, and this is Kate is nothing like this is a vector. That is the element of the vector space. This is actually what forms the vector space, and if psi is an operator, that is the linear transformation operator, then we denote it by the bra function. That is this is what actually this the thing, and and I don't know why I just started. So anyway, actually this is not a linear transformation in the sense. This is a linear transformation from the Kate space. Say that is called let that be called capital K, and this is Kate space to R. This type of function are called the linear forms, like vectors, a linear transformation that plots capital vector space to R actually. To R or C. Should be C, I guess. Should be C. Or I don't exactly remember. Like, so this is a linear form actually. So this is a special kind of vector space, and that is where the Schrodinger's equation comes out. That is, this is the wave function, and whose modular squared gives the probability actually. So anyway, let's just move on to Hadamard matrices. This is something that I might know a bit. So this was I haven't mentioned this on the notes. I haven't mentioned this on the notes. I mean the differential equation part. So we'll try to add that. So Hadamard matrices is like okay. So let's define. H is a matrix and 3 points plus minus 1. All entries are of the form plus minus 1. Okay, so the all entries are of the form plus minus 1. The consider any row vector, right? Row vector. Length of this row vector, that is the Euclidean norm with respect to the Euclidean norm, that is summation a11 squared plus dot 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 a1 n squared, a square matrix of course n plus n, equal to root over n. N is the order of the matrix, and okay, so and the row vectors are orthogonal to each other. So now, can anyone you all can visualize it, right? What I meant by row vector length equal to root over n, matrix
Yeah.
entries plus minus 1, and they are orthogonal. Like, so basically, if we consider a11, a21 plus dot 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 a1n, a2n, it should be 0. Okay, so here's an interesting thing, that is okay, claim this is an easy claim. Claim order of H Hadamard matrix is of form 4k.
Wait a second. I think one of these was like an ISI entrance test problem from a couple of years ago.
Actually,
Yeah, I remember this one.
something like permutation of that matrix. Anyway, so now this is relatively easy to prove. Like, just okay. Like, I must mention the credit goes to Apostle Calculus Volume 2, and the exercise is given in the something like the book right now. I just see this. Goes to just Oh, wait a second, just 1 second. Meanwhile, you can try to prove this. Like, this is simple, but still. Actually, the converse is the open problem. Also known as the Hadamard's conjecture. Okay, I messed up. I couldn't find it. Sad, but okay. Anyways, it is there in the Apostle Volume 2. So, anyways, you got the proof, right?
Yeah, I have proved this one before. I've come across this problem before and proved, and I'm actually looking for where I took it down. Like,
Okay, so just
yeah.
so this just comes with two observation. Like, if okay, now the row element x1 vector and x2 vector. These are the row vectors of this H, right? So this H has all the known properties. There is plus minus 1 rows and the length are orthonormal. So we can just write that x1 y1 dot x2 y2 y1 equal to x1 y1 vector plus x1 dot y2 vector. This is just one mod squared. So this is n in this Hadamard case, in this Hadamard matrix case, right? So cause x1 x1 dot y1 is orthogonal 0, x1 dot x2 is again 0, y1 dot y1 is the only term that's non-zero, and y1 dot x2 term is again 0, and the length of this y1 squared mod is n. So this since the Euclidean norm is root over n, so this is n. Now this is one observation, and another observation is again trivial, that is consider the ith element plus okay, so ith element now since just consider the ith element of this y. Okay, so y1i plus x1i dot y1i plus x2i. Okay, so this is nothing but this is either 0 or 4, right? Like it can be plus minus 1, it can be plus minus 1, so either 2 or so since this y these are same, this both are same, so like plus 1 minus 1 0 plus 1 plus 1 2 plus 1 minus 1 again 0, so plus 1 plus 1 2, and if this is minus 1 again, this should be minus 1, and this if it is plus 1 it's again 0, and it's minus 1 and it's again minus 1, so 2 minus 2 into minus 2 go to 4 again 4, so it's either 0 or 4. So basically the order now this is nothing but only writing this thing as component wise and then actually summing this, so like it would be basically 4k, so equal to n. So basically the order of the matrix is 4k. Now Sylvester somewhat found the explicit Hadamard matrices for k for n equal to uh, 4, 8, 16, 32. But the open problem is, like, for every k does there exist a Hadamard problem, Hadamard matrix? That is the open problem. That is the Hadamard's conjecture. There do exist. This is the conjecture. Of course, this is an open problem till now. So that is a nice research opportunity in this topic. So,
Shrijan, this was an ISI 2018 UGB paper 8th question. I like when I was preparing for the exams, I'd solve this one, but not with a clean approach like the one Bijan just presented.
I did something like first I proved n is divisible by 2, then I proved n by 2 is divisible by 2.
Yeah,
but
exactly.
I,
Yeah.
actually I wasn't probably that aware, but I was also stuck at that problem. I discussed with one of my uh, one of my senior at CMI. So and I was trying for a matrix based approach for that problem. Is that directly a matrix problem? Like, I don't think so. Like, right, there's a combinatorics
No, it was a
recursion.
matrix problem. It
Okay,
said that
I might be
it
missing
said
out.
that any two rows of the matrix, like any two rows of the matrix, have to have dot product 0. I think.
Okay.
Yes.
Okay. So that was probably like all the entries are plus minus 1. So yes, any two so dot product 0 or 4. This was the question, right? Like, or there were some additional conditions and they somebody excluded the 4. Or
Huh?
okay, okay, this. So this is correct, right? Like the matrix of order. Uh, if this Hadamard matrix has order of the form 4k, but the question is the converse, like, to prove the converse. So yes, this is an unsolved problem. And so, are there some cool properties of Hadamard matrices? Actually, Hadamard matrices are somewhat used in the optimal coding of methods of space communication. Like, so, anyways, so and some other cool properties of not that cool. So, anyways, so H transport is equal to H transpose equal to some n times in. This is easy to see, right? Like this one with this one, these are basically the same, and this is basically the norm of uh, this. So this, since the root norm is root n, so basically is n dot dot dot. So so this is simple to see, and again this gives the determinant of the Hadamard matrix, that is equal to norm h squared equal to n power n, but n implies mod equal to n power n by 2 plus minus, right? So again a cool property that Hadamard matrices are not, like, what to say, non-singular for n equals to 0. I don't even think that this would actually there's a degeneracy in n equal to 0 case. So anyways, n greater than 0, so that's the thing. Like what's a matrix then? N equal to 0. So okay, so for n equals to 0, this is this forms a non-singular set of matrices. So that's all. Thank you for bearing with me and listening.